Hello, ladies and gentlemen. Thank you for the opportunity to present our idea in front of you. My name is Stoil Ivanov. I'm from the Sofia University, and we're going to talk about the idea which represents end-to-end mission, and it's a framework of activities that can be applied as proof of concept using small satellites. Today's presentation will cover the following points: the need, the mission objectives, concept of operations. We're going to point out some risks, and we're going to finish with some conclusions. Space debris, we all know what it's about. Space debris is mainly consisted of decommissioned satellites and upper stages. Only 6% of the orbit population are operational satellites. And one of the main reasons for those satellites to get broken in small pieces is the explosion of tanks with still some fuel left in them. And it is believed that more than 600,000 objects larger than 1 centimeter were created that way. Our mission is divided in two submissions: the observer submission and the aggregator submission. The observer submission is the long-term submission from 3 to 5 years. We're using our satellite, the so-called observer, to scan the debris, and the observer sends the data to the ground station. And just a second, some menu here. Ground station, and the ground station uses the data, analyzes the data, classifies the debris by their properties, and estimates the aggregation mission plan. After we come up with particular mission plan, the aggregator submission starts. This is a short-term mission, which is planned to be from a few days to several months maybe, and because we need the fast method of delivering removal missions, we propose the usage of the so-called air launch method, which uses a spacecraft instead of a launch pad and first stage rocket. In this way, the spacecraft can be equipped, the aircraft can be equipped with a much smaller carrier rocket and can bring satellites for like 40 or 50 kilograms to altitudes of about 1,000 kilometers. After the air launch is executed, our aggregator, again our satellite, gets the debris, and afterwards the deorbiting event takes place. So we're going to focus on the two satellites that we have, the observer and the aggregator. The first is the observer. The observer can be equipped with lidars, optical telescopes, multispectral camera, and because of some studies of ESA and NASA, it is believed that the largest debris density is on the inclination between 82 degrees and 85 degrees, and altitudes of 800 kilometers and 1400 kilometers, which shows the following orbital parameters for the observer. The orbit type is circular, the inclination is 82 degrees, and the altitude is approximately 1050 kilometers. We equipped our observers with lidars with 400 kilometers range and 20 degrees cone angle. Following these considerations and these parameters, we run some simulations created by us. And here on the left-hand side, you can see 6 observers with 2 lidars pointed at Earth and opposite direction. And on the right-hand side, you can see 3 observers with spinning lidars, which spin around the velocity vector of the observers. The debris data is taken from NORAD and represents the scattered parts of 3 satellites, Iridium and Fengyun. According to these simulations, the gray points here are the undetected debris, and the red points are the detected debris. And this is just after 2 days. We run quite a few simulations with different regimes of the lidars, and we came up with just some. I'm showing you just some of the results. You can see that 6 observers with spinning lidars saw the designated debris, designated debris targets. So a little bit more than 90% in about 2 days. Okay, we know where the debris are. We have successfully planned aggregation mission, and then we have to aggregate it. This is where the aggregator kicks in. Its job is to actually aggregate the debris and deorbit it in the upper atmosphere layers of the Earth. The aggregator is consisted of 5 autonomous units, which are packed in a single unit, and the total mass of the whole aggregator plus the payload is approximately 50 kilos. And the payload is a specially designed net made of the well-known Kevlar, for example, or carbon fibers, or some novel materials like graphene, nanotubes, and others. And the considered net side, this is the distance between 2 adjacent peripheral satellites, is approximately 140 meters. So the aggregation is executed as follows. On figure A, you can see the packed aggregator on a little bit above the target debris group, which may be a cloud of debris or just a few larger objects. Then the deployment of the net takes place, and the whole configuration slowly goes down and enters the debris cloud. So the debris is actually entering kind of from the behind of the net. And after the mission is completed, or the cloud is cleaned, or the net is full maybe, we close the peripheral satellites to secure the debris in place, and we can think about the orbit event. Well, this looks like a stunt fun, like a fun stunt, but does it work? Well, we wanted to check if this configuration is doable in such way. This is why we run a simulation showing the whole configuration. Imagine that the net is already deployed, and we wanted to see if the configuration is stable. Well, as you can see, it quickly distorts. The satellites, the bottom satellite is faster than everyone else. The top satellite is slower. This is simple orbital dynamics. And the 2 satellites, which are in parallel with the retainer in the middle, will just oscillate around it because the orbits will intersect. Well, we thought about a solution for this. We cannot count on engines always trying to correct the positions. So we wanted to think about something else. And we thought, well, maybe this simulation doesn't work because the satellites are not with the same initial orbital parameters. Well, after that, we thought, okay, let's show it packed and then spread the peripheral satellites. And this is what happened. Unfortunately, still it doesn't work. It doesn't work because the bottom satellite is still faster and the top is still slower. It just doesn't work. So we're thinking of fixing this, and we came up with the following proposal sequence. I'm going to show the path of only one peripheral satellite because it will be clear for everybody to see. So in a given moment 0, the peripheral satellite is pushed out, maybe with a spring, and the thrusters are turned on. The direction of the thruster of the peripheral satellite is perpendicular to the line between the central master satellite, the so-called retainer, and the peripheral satellite itself, as it is shown on the figure. So these actions that we take will create a spiral motion, and the peripheral satellite will continue to move away from the retainer in the middle. So in moment 1, we maintain the proportion and we continue the spiral motion. At the given moment 2, we reach the net size limit. That means that the net will be stretched and tension force will appear on the peripheral satellite. But because of the movement, the circular movement, also this force will be always available, and the satellite will continue to revolve around the retainer in a stable manner. But is it actually true? Well, we have a way to check this, and we run the following simulation, giving some angular speed to the peripheral satellites, and yes, the configuration is stable. I would like to say that this is a near stable configuration because we didn't consider the solar pressure and some other distortion effects like moon's gravity, sun's gravity. We believe that it is stable because the peripheral satellites have equal average paths and speeds. It's like we're looking at the same satellite in different moments of time. It will not distort. So, because of the effects that we did not consider at first, a more precise simulation is yet to be done, and we want to execute the whole formation and maybe at the end closing the net as well. We admit that the testing for the net on the surface of the Earth is a bit difficult with the gravity. This is why we run a simulation of the net itself as well. This is a simplified net with simplified stitch pattern, but the sizes of the segments are increased, and this is what we came up with. And by doing so, we believe that we can judge about the stability of the whole configuration, because the circular motion of the retainer of the peripheral satellites around the retainer creates bigger tension force. So as fast as we rotate the peripheral satellites, the bigger the tension force will be, and the more stable the configuration will be. It will be harder for space debris to disturb the whole configuration. So someday we'll continue with actually throwing space debris with this net. This is not a simple job, so it will take some time. Of course, almost nothing in life comes without certain risks. In our mission, we have risks. One of them is the complex mission planning of the aggregator's flight. Another risk is the difficult and risky deployment and closing of the net. It's a big net, it's a membrane structure, it's difficult to predict sometimes what will happen. And of course, possible net breakage. Maybe if the net breaks, we will probably create a bigger problem than we were trying to solve. So this is a serious issue. We have to be careful with unpredicted debris collision. Of course, unpredictable behavior of the captured debris also exists, because as I mentioned at the beginning, one of the main reasons of creating small pieces is explosion of tanks. What if we get the tank and it explodes in our net? The conclusion is that we proposed an end-to-end mission with small satellites, which can also be used as a proof of concept. And someday maybe this mission can be scaled up with bigger objects, bigger satellites, larger clouds of debris, bigger energies. It's a novel concept for satellite constellation stability. And of course, this stability cannot be achieved without the so needed swarm intelligence of all the peripheral satellites. By their combined effort, they have to try to recover the whole configuration and resist every disturbance disturbance caused by the debris. Thank you.
We have 10 minutes for question.
Your aggregator mission to detect the debris, it seems quite impossible to me to do that in a vastness of space, to detect a very small piece of debris with using a LiDAR. If the debris is traveling relative to you 20 kilometers per second in a different orbit, how are you going to detect it in the first place, and in the second place determine the orbit of that piece of debris? Because it's not a stationary thing that you're detecting, it's something that moves with orbital dynamics. So to me it seems more possible to use radar systems on the ground to detect the debris, determine its orbit, and for you to do the planning for your recovery mission to send and recover the debris. Can you comment about that? I'm not sure from your presentation how do you envisage detecting the debris and know exactly where it will be in a week, 2 weeks, 3 months, 6 months from now, before you go and collect the debris?
Well, this is why we introduced the observer mission. We believe that we need in situ detection and further observation, so we can, with time, we can precise the position of the debris. If we see the debris in different moments of time, we can estimate the orbital parameters.
No, that you have to do. I mean, the debris is not stationary, it's moving.
Yeah.
And LiDAR, how does the LiDAR work? Do you look at the reflection from the debris to detect it?
So can I repeat
the LiDAR, how does it work? Do you look at the reflection you receive from the debris?
Yes.
So it may be quite a faint signal if it's 2,000 kilometers away, traveling at a huge distance, and giving you a very small area to reflect from.
Well, the LiDARs in our proposal are with 400 kilometers range. We consider everything farther than that, not detectable. We have to probably put the observers in different orbit to cover different region. But I don't think we can see 2,000 kilometers away.
No, I mean, within 400 kilometers from you in orbit, there may be no debris, or very small pieces of debris, undetectable pieces. So it's not that you will see a cloud of debris within a 400 kilometer radius around you. But okay, I don't want to elaborate too much on that.
Well,
the net story at the end, I think it's highly improbable that you will catch more than one piece of debris, because they all move in different orbits, except if it's a cloud of debris.
Yeah.
But that quickly disperse in any case due to difference in drag. So what is more probable is that you will send a mission to recover a certain big piece of debris and recover it by using a net. But that also means that you have to be in exactly the same orbit, so that the relative velocity between you and the debris set that you want to capture is about the same, so that you don't break the net. I mean, otherwise the net must be infinitely strong.
Yes. And this is why we planned the mission using the data from the debris. I mentioned that we can use it for, catching larger objects. And the debris cloud, of course, if a satellite breaks, it will spread around Earth due to, different effects on each piece. But it will take time. And this is why we introduced the avalanche system to, send the removal missions in the matter of a few days after the breakage is detected. For actual debris cloud to spread, bad enough so we can't get it, it takes a couple of months for it.
Yeah, and I understand that this project is in the concept phase,
yeah,
basically. And can you just summarize the main edge points? Like what type of or what size of debris are you going to detect, and what is an aggregator the mass or volume what you want to recover and bring back to Earth?
Well, the sizes of the objects with the currently dark, which is it was developed by another team, and it was actually presented on MIG in previous years. Detects 10 centimeters large pieces, yeah, on 400 kilometers range. We're thinking of maybe the aggregator is 50 kilograms, 20 kilograms net, 10 kilograms retainer, 5 kilograms each peripheral satellite. We believe that we can get a lot of debris. That depends on how fast the debris will enter the net. And again, it's a subject of the mission plan. But if there are 50 kilograms of debris, we may be able to get it and dive into the atmosphere.
Okay, yeah, thank you. Some more?
Okay, so maybe the net is deployed and some debris will go into this net, and then maybe if the different speed, difference of the speed, relative speed is very large, maybe the debris will give a lot of impact to this net, and then after that maybe for satellite and the net dynamics will be very much complicated. So did you do that some kind of the analysis, dynamic analysis of this kind of net movement?
Well, this is not a simple task, and fortunately there are no softwares which can do that right now, specialized softwares. We have to develop our own algorithm, which will take time. I hope someday I will present the results to you.
Okay, maybe it's a very good research thing.
Yeah, I think this is enough for a PhD at least. And I just wanted to mention that we believe that we can recover the energy, because if debris enters the net, it will give off its kinetic energy, and it will, it will try to disturb the configuration. But by this angular velocity, this circular motion of the retainers around the peripheral satellites around the retainer, we believe that this can recover the configuration. So this can be, we can judge about the stability.
I just want to re-emphasize the idea of going after big objects.
Yeah.
I think that the biggest threat right now is big objects becoming small objects. And I think the idea of going after them once they break up puts you in a very bad ConOps mode, because you have to find the launch at the right time, and you need to go up and get there before the cloud gets too large.
Yeah.
If you change the ConOps and you say, I'm going to go after big objects before they break up, and you plan it, you catch one object and bring it back, the benefits to the debris situation is huge, because you're taking away potential big clouds. So I think if you focus on something like that, you have a very good plan. And it eliminates a lot of complexity. You don't need the observer satellite, because the big things you can detect easily. You don't have to worry about, once you impact with debris, you don't have to recover. So, and it's not like you're giving up on benefiting. I think you're doing a great job at removing debris. So I like that idea.
Thank you.
So we have 1 minute. So do you have any questions from the audience? Quick question? No? Thank you.